That'll work too.
Oh yeah, you said you work part time. You said that. Now you beginning this week.
I work last spring too.
No, I'm saying you told some companies that you work part time. You work part time.
You told me about
You said it too. What did you say?
told me about
You said yesterday. You
no,
said something.
it was yeah.
Oh yeah,
The first sergeant asked us who works.
No, yeah, he said who works.
Who works part time.
You do now, soon you begin.
I worked all last spring too.
What you mean? It's just like a church say, he's I don't know if you
No, that's like asking me if I was
All right.
season right now.
So today we talk about attitude control methods. Okay. And their capabilities, right? So the first method we'll talk about is there are various methods. Gravity.
Brother, son,
Yes.
when are you gonna take us to a flat lab so it shows how we make this up?
Sure. So we'll try to do that next week. Okay. Next Wednesday. The following Wednesday.
That isn't.
Hmm.
Oh, no, I thought that's what that word was.
So gravity gradient and
There.
That's what I thought it was, but we gotta have a week.
Wednesday axis.
axis. Yes. Okay. We'll talk about this and we'll talk about gravity gradient with momentum bias wave.
This is very limited, right? This is very limited.
Yes. So the typical arrangement is such that
The second one says gradient versus momentum.
with momentum bias V. Okay. So look up this satellite. Okay, here. You'll come across, you'll understand what gravity gradient means. Okay. If you just look at a picture, you'll understand what a gravity gradient means. Okay.
That's satellite.
That's a satellite. GeoSat, okay, mapping Earth's shape. This was one of the very early satellites. Right?
But you want to look that up?
Hmm?
You want to look that up?
Look it up. Look it up. So it had this configuration. So you have there were solar arrays deployed like this, and there was a camera inside, right? And this was the Earth's surface.
That's a satellite user?
This is a satellite. Okay? It had a long boom. Okay. And this was, what direction is this?
Native.
Yes. I want you to tell me this. Okay. So this is the nadir direction. Eventually, what happens is it will align like this. It gets launched. All right. So here, what you're going to see is the satellite, of course, is not going to do. You cannot launch it like this, right? You cannot launch. You have to understand that any boom cannot be launched in a deployed state. Everybody understands that? Is that clear? The boom has to be in what state when it gets launched? Use these words. Learn the use of these words. Stored versus deployed. Okay. You have to I'm sure many of you realize, especially who have taken my course, the words you use as space engineers are very crucial. Okay, they change a little bit, although it may mean something very basic, but you have to learn to use those words. Only then you're going to get into that word. Okay? So stored, you understand what stored is, right? Everything is stored. Okay? Everything is undeployed, so to say. So it is stored, and once it goes up there, there is deployment happening. You got it? And if you want to be a good spacecraft engineer, all right, or this is one area, mechanisms. You see, one of the best things about the any satellite for that matter, but if you look at the James Webb Space Telescope, right? The James Webb Space Telescope has a big deployable. Have you seen a picture of a James Webb Space Telescope?
What's it called?
James Webb Space Telescope, JWST.
Can we use our phones to Google it?
Yeah, Google it and see.
You said it has a big what?
Deployable.
It's on the aluminum sheet that's on
Yeah, it's not an aluminum sheet, it's actually mirrors. Okay. And what you're going to see is
What is it? Protection from outside.
it's actually for collecting, those are a certain very specific type of mirrors. Those are for collecting information. Okay, it is not necessarily protection, but it is collecting information. And you cannot, if you see those mirrors, if you still had a chance, go by Goddard, and one of those mirrors is still there. It was hexagonal mirror. So the entire thing, if you look at it, it's multiple hexagons, right? Did you guys see that?
Oh, which one is the blue?
The mirrors are, you cannot deploy them like that. Okay? So if you see, sure. I'll just pull it up. Alright, just look at that, okay? Don't just don't use it as an opportunity to just keep texting or. Alright, look at this, okay? So if you see each of those, you see what that configuration is, right? That's a communication device, the mirrors, and of course, you see these are also deployed. This is the protection sheet. Okay? And those are the mirrors. So they used, for these, they actually used, or they got this idea from origami. From what?
Origami?
Yes. The Japanese art of paper folding. So they did that. So mechanisms, when you do mechanisms, so this mirror is used for, what happens is all that information is bounced off of those mirrors, and you see that thing, that's the receiver. Okay, that collects all the data, and it essentially, that data is processed. Okay. But if you look at this, or for that matter, any telescope or any satellite, there's a lot of deployables, and there's a big career. You can be really, really creative with deployables. You could make a real career out of designing mechanisms for spacecrafts.
Can they be beautiful?
Huh?
Can they be like compacted back while in space?
Yes. So there are provisions sometimes where you put them back, open up them back. For example, if you launch a rocket, it used to be launched with heavy swings, not swings, but strings of masses attached, and that used to swing. So that would stabilize it would not tilt, and once it went up, it automatically retracted. Okay, so you have to have that understanding. Now, here, if you look at any gravity gradient satellite, this is a control thing, okay? A control method. So you can say this is what happens eventually. Okay? And you can see a typical gravity gradient may look something like this. You see the satellite is here, alright? And there's a big boom. The satellite is here, there's a big boom, and there's a very, very heavy mass attached to the end. And what you typically do is you have to have that entire thing deployed or stored when you launch it, and you it has to come out. Now, it is not like what you see in ground. Okay, so when something gets launched from ground to space, what happens? What changes? the temperature changes significantly, right? There is cold welding, the pressure changes significantly. So when you design, you cannot do a design which is going to work in ground may not work in space. So you have to be very, very adept with that. And you can get really creative with mechanisms. Alright? So here you can see that where does this point? Earth vertical, local vertical. Okay, local vertical is what? If you have, if this is Earth, right? And this is your orbit, what is this? This is the local vertical. Local vertical means wherever the satellite is, okay? This is the local horizontal, and this is the local vertical. You got it? It will always be in this.
So this is wherever it is at the time.
Yeah. When it is, if it aligns like this, it will always be like this when it orbits. It keeps on orbiting. You get it? So if you have a camera here, it will always be pointed toward. That's a needle pointing satellite. And the accuracy of such a satellite, the attitude accuracy of such a satellite is 5 degrees. Alright? So it will be off by plus or minus 5 degrees. What is the, if I give you a question, by how much angle does such a satellite rotate for one orbit? By how much angle does this satellite rotate for one orbit? Hmm? 360, correct. So it will be like this, right? It will do this and it will come back to that. It will rotate by 360 degrees. Alright? So the rate is what? The rate. 360 by orbital period. Right? Orbital period. Whatever the orbital period. Okay? Plus or minus is what? So if it is always has to point to Earth with respect to the local vertical, it will be off by plus or minus 5 degrees. Okay. 2 axis. Why does it say 2 axis? What do you understand by 2 axis? Anybody? What is the meaning of 2 axis? So think about this. If it is like this, right? This rotation, you cannot do anything about that rotation. Do you understand? This axis or this angle, you cannot do anything about this. It's stabilized about this axis and this axis, but not this axis. It's only 2 axes. You got it? So it's stabilized about only 2 axes. Now, gravity gradient with a momentum wheel. What you do is, you have a wheel here, not here, in this direction. Okay, it will be somewhere here only. Alright? Or it will be, so you see, then if there's a wheel in this direction, in this axis, you understand? And if it is spinning, it will make sure if the wheel speed stabilizes, there will be no rotation. You will achieve all 3 axis stabilization. Does that make sense? So here you have a gravity gradient with momentum wheel. Alright? You can only do, the gravity gradient will take over. You cannot do that. You cannot do this with the wheel. But what you do is, you have this, right? So this is the gravity gradient. Okay? And the wheel is about this axis now. And the wheel will be spinning inside. You got it? If the wheel is spinning inside and if the wheel reaches a constant speed, the satellite will not spin. Only when the wheel is changing its speed, what will happen is the satellite will spin in the other direction. You get it? But if the wheel reaches a constant speed, the satellite will do this. The gravity gradient will maintain it like this. Now you get 3-axis stabilized, and the stability you get about plus or minus 5 degrees. Got it? Let's look at pure spin stabilized. Okay. This, or before that, let's look at this. Passive magnetic. Okay. Here, where will it align with pointing options?
Dr. Sun,
Hmm.
what do you have written after momentum, gravity gradient with momentum?
Bias.
Bias?
With momentum bias, yeah. Passive magnetic stabilization or control. If you have a passive magnet, what does a passive magnet mean? A permanent magnet, okay? Which cannot, if you have a permanent magnet on a satellite, what's going to happen? It's going to align with magnetic north-south. That satellite is eventually going to align with magnetic north-south. Now, what is the limitation of, you will get, where will it align with? It will align with magnetic north-south, right? What is the limitation of such a control method? A big limitation of this. What happens when it passes through the poles?
It's going to change direction.
It'll flip. Okay. So if you have, so if this is the north pole, right? It'll be pointed like this, correct? It will go like this, and it's doing this. It will flip. It's this thing when it goes to the pole. Okay. So if it is pointed like this, it will not point like this. It now has to do this. It will flip its direction when it passes through the pole, and again it will flip its direction if it's passing through the south pole. Okay. So only if you have an equatorial orbit, it will always remain like this. You get it? If it's an equatorial orbit, this is aligned with north, this is aligned with south. That will remain the same. But any inclination will make it flip a little. Okay. Here also, if you have north-south, always try to understand this. Can you do anything about this rotation? If it's doing this, right? The magnet is here. You cannot do anything about this rotation. The rotation about that axis, you cannot do anything. You got it? If it rotates, it will keep on rotating about that axis. How do you counter this? Wheel. You again put a passive magnet and a wheel about this axis. It's difficult to determine where the wheel will be.
So this is a passive magnetic with momentum bias.
No, this is just passive magnetic. If you put a passive magnet with momentum bias, you'll get 3 axes. Okay. If you have both, you'll get 3 axes. But just with the magnet, you'll get 2 axes. Alright. Then you have pure spin, and I'll show you this. Pure spin stabilization. Inertially fixed can use, so here, let me talk about this a little bit. But the accuracy you're going to get is really, really nice. You get plus or minus 0.1 degree to plus or minus 1 degree. In 2 axes. Okay.
What did it say? Initially?
I'll say inevitably or initially.
Inertially.
Inertia.
So because inertially fixed, okay, about 1 axis. So if you have a pure spin stabilization, all right, what is spin stabilization? Spin stabilization is anytime you put a wheel in a satellite and the wheel starts, once it starts spinning or once it reaches a steady rate of rotation, the satellite, if you see, if you want to stabilize anything, okay, if you spin something inside, it is very difficult to move that, or that if you want to disturb it, the spin is going to try and reject that. You understand? So you have this spin stabilization. Okay. The accuracy, because there is, if you design really nice wheels, and this is again an area of spacecraft engineering you can pick up, designing very nice wheels. Because when you design wheels, what is the issue with wheels? Friction is an issue with wheels. Okay, and it's particularly in space, you cannot use lubrication. Okay, it's very difficult to use lubrication in space. You have to use bearings without lubrication. You have to figure out how to use them. And the big challenge is once you spin something in space, it's detrimental to stop it and then retry to spin it again. What happens when you spin it? The satellite will start spinning in the other direction. Okay? Once it stabilizes, the satellite will stabilize. Now, if you stop it, as the wheels slow down, the satellite will start moving. It will gain momentum, it will gain angular momentum. When the wheel stops, the satellite would have gained a lot of momentum. You understand?
Yeah.
And it's very difficult to manage that momentum after that. So if you spin a wheel, you potentially end it spinning continuously for months together, even years together. So there is a bench test for wheels, okay, and this is where you can design, you can get very creative with wheels. There's a bench test in the spacecraft industry where you design wheels, you start them, and you keep them for years together. You understand? They're running. Every time you come to office, they are running. You go back home, they're running. You come back, they're running. And they are not getting heated, they don't have lubrication. You understand how difficult such a design would be? And then testing it, right? So such a wheel, what is the limitation here is you get really good accuracy, but one wheel, pure spin stabilization, you have one wheel, you get 2 axes. Okay, those 2 axes. Alright. Then you have dual spin stabilization. So here, what we are talking about pure spin stabilization, okay, we are achieving this. We are not really using bias wheel or momentum bias wheel. We are using propellant, okay, to achieve this. How would you spin using propellant?
Fire in one direction.
Huh?
Fire in direction.
Fire in that direction, okay, and you counter in whichever direction it is spinning, and you fire the propellant to counter that spinning. Okay, here you are using propellant, and the accuracy. See, propellant is used for what will propellant create? It will create thrust, right? The escape of propellant. Okay. When will that thrust become? What kind of? Are we really interested in thrust here, or what are we interested here? We are interested in torque. Okay, all this is torque. Does that make sense? When does a propellant result in thrust, and when does it result in torque?
And it results in thrust when you're like, okay, in this case, when your thrust is in line with like center of gravity.
Yes, absolutely. So when the thrusting force is in line with the center of gravity, it will create thrust. If it is off of center of gravity, it will create torque. You understand? So the thrust, the propellant can be used for both attitude control and orbit control. You understand? If you want attitude control, you use the off center of gravity thrusters. Okay. If you want orbit control, you use thrusters which are aligning with the center of gravity to push it away. Okay.
So attitude control is going to use thrust. Is that what you just said?
Right. So the thrusting power is essentially if you thrust and the thrust is if it hits like this. So you have thrusters if it hits like this, it will create torque, right? If it hits like this, it will create motion, linear motion. So that will create orbit control. If you are doing this, if you want to do the Hohmann transfer, right? You get here, all right, and you fire thrusters here, so it will go in this. You get it? So thrusting force has to align with, or it has to pass through the center of gravity of that system to create linear motion. Okay. And there is dual spin stabilization. So this is these two, we'll discuss this a little. For what we are studying, we may not have a whole lot of scope for this. Okay, this one and this one. So we'll talk about this. Right? Overall, we'll talk about this, but for CubeSats, it's very difficult to carry. This is a big question mark. Okay? So we'll talk about bias momentum. So here, it is best suited for local vertical pointing. Okay. What you can achieve is again plus or minus 0.1 degree to plus or minus 1 degree accuracy. Okay. Concern is life of bearings. This is a very critical concern. And whatever we are going to do for the space grant satellite, we have to look at what kind of attitude control we need. Okay.
How many axes?
Hmm?
How many axes?
So this depends on. Typically, what happens is whatever axis it spins. Okay. Off of that, you cannot disturb it. Okay. So here you can say it is each wheel will give you like 2 axes. There can be really only one wheel. If it's a momentum bias spin stabilized satellite, there is one wheel. Okay. Many satellites were launched like this. Okay.
This is life of beams or bearings.
Life of bearings. Okay. That's a concern.
Is it the dual spin stabilization?
Hmm.
The last
Hmm?
2 different kinds of bearings.
Yes. These are 2 different things.
Did we finish with dual spin stabilization, or is that just the same?
I'll talk about that later. Leave these 2 for now. Okay, we'll talk about this a little later. I'll talk about this. Next class I'll talk about it. I want you to discuss, think about these a little bit more, because what we want to do is we want to involve ourselves in a space mission as soon as possible. Okay, and there is, and I don't think this is an option for us. We may not be able to carry propellant because of. Typically, what is the concern with the propellant? If the propellant is heavy, and what happens is, if there is anything, if you don't design propellant, so what is the issue? How do you pack a propellant?
You got board tank.
You put it in a tank, right?
So it's something wrong with the
What do you know about in the tank?
pressure.
Pressure, right? So what pressure do you pack it at? Atmospheric pressure, right? It is always packed at atmospheric. Keep in mind, you remember the pen problem, right? The ink pen problem, which was faced in the resisting space. What happens if you pack an ink pen and send it to space? Ink will flow, ink will spill. Because what do you pack it at? Atmospheric pressure. The pressure there is really low. Where does energy flow from? High potential to low potential. Okay, so when you pack something like that, when you pack a propellant, you have to pack it much higher than atmospheric pressure, right? Because it is a pressurized tank. Okay, and these satellites we are going to work on, they don't fly by themselves, or they don't have their dedicated launch vehicles because of the size. Okay, there is no. There are companies which are coming up with dedicated launch vehicles for CubeSats, but there is no dedicated launch vehicle right now. If we are going to go through, let's say, NASA. Okay, what we'll do is, if somebody is going, okay, we'll just tag along, and then wherever that somebody is going, wherever that primary is going, that primary will drop us off. You understand? And if you are going along with the primary, what is the priority? The primary is a priority, right? So we have to make sure Now, there is nothing in the satellite which will potentially impact the primary, and propellant is a big concern. Okay, so they typically have not allowed propellants, chemical propellants at least. There are electrical propulsion, and that has triggered a lot of research in electric propulsion. Okay, so CubeSats are not quite allowed to pack chemical propellants with them when you're going with a secondary payload. Okay. So that's the reason I'm saying what we need is we can do, of course, if you want to go to a lunar orbit, right, we cannot expect somebody to take us to a lunar orbit. You understand? We have to do that on our own. No primary satellite is going to take you to the lunar orbit and then throw you there. Launch vehicle definitely will not go up to that point. You understand? So what we need is, we need some kind of propellant, but probably it will be electrical propulsion. Okay.
Electrical propulsion.
Hmm?
Electrical propulsion, like what?
Basically, it's what you do on jet fuel.
Well, I'm saying like what's in the form of electrical propulsion?
It's photons. It's ions, sorry. So what is going to happen is, it is going to shoot ions like it is shooting.
So it moves mad slow. Will it move like really slow?
Yeah, it'll be gradual, but it will do its job. For example, the mass, the rate will be pretty high, but the mass itself will be
Slow.
relatively low. You got it? So you cannot throw out as many particles or as much mass, but the rate will be high. You get it? So essentially what happens is, you have to understand, and I've talked about this in the past. We'll stop here, okay? So if you understand Newton's law, Newton's second law, it is d over dt of mv, right? This is force, and this is change in momentum. Okay. So if you split this, or if you take the derivative, you're going to get ma plus m dot v, right? That is a product rule. If there is negative mass loss, so what it's saying is, you have to understand, force only does not create momentum or change in momentum. Change in momentum is also capable of creating force. You got it? This does not necessarily come first. You never really know which one comes first. You understand? How do you create force? You change in momentum. How do you create change in momentum? Through force. Okay. So here you have to understand that when you split this, right? Of course, velocity and acceleration is going to create force. That is, it's pretty evident, right? But what you have to understand is change in mass, rapid change in mass. This is change in mass, right? Mass flow rate can also create thrust. You get it? That is how propellants work in space. Rapid change in mass. You're rapidly throwing mass. Okay? So this is negative, right? This becomes negative because it is losing mass. You understand? If it is losing mass because it is throwing away stuff, right? If it is losing mass, that causes thrust, force, and that is what triggers the satellite off. You understand? So if this mass is chemical, the mass itself is more, but the rate may be not that high. But if it is photons or if it's ions, okay, the mass is not a whole lot, but the rate is high. That also creates force or thrust. And that thrust is going to create momentum. You get it? So stop here.